In our third part of probability, we're going to talk about expected value. And the expected value is going to be based in this concept called the law of large numbers. All right, so let's think back to the things that we have talked about. Generally speaking, there's two types of probability that we investigated. There's a third type, but we're really just going to think about two of them right now. We had experimental probability and we also had theoretical probability. Now I refer to one as experimental probability and they're going to call it here relative frequency probability, but they're the same thing. Experimental probability is based on things that have actually happened. Sometimes it's looking at old data, or sometimes it's looking at something at the time that's happening, like maybe somebody in basketball and them shooting free throws and how many they make versus how many they don't make. Theoretical probability is looking at all the possible outcomes that are available and the number of outcomes that we find favorable, and then designing or creating like a fraction or some number that represents the probability of those favorable outcomes out of all the possible outcomes that we have. All right, so the law of large numbers tells us that even though we know that when we do like an experiment, let's say that we take a coin and we're just flipping a coin over and over again and looking at heads or tails. When we start flipping that coin, we shouldn't think it's weird if maybe you flip it 4 times and it lands on heads all 4 of those times. It can happen because the likelihood of it landing on heads or tails is equally weighted with each other. So when that happens, it's not that big of a deal. But oddly, almost like oddly, but it's true, and you can do the experiment with this. If you were to take that coin and flip it 100 times, and you start counting how many times you get heads and how many times you get tails, the numbers are gonna start sort of gravitating towards like 50 and 50. It might be 40 and 60, it might be 45 and 55 or something like that, but the numbers are going to start. So even though you might start with a streak of heads, you're going to end up getting some tails in there, and you might have a streak of tails at some point, but eventually it's going to start getting closer and closer to an equal balance in it. You might not see it at 100 times. It might end up being like 40 and 60, where there's still a pretty good difference in it. But if you carry this out 1,000 times, then you're going to get a little bit closer to 500 and 500. Okay, the law of large numbers is going to state that as we conduct an experiment more and more times, as we keep doing it, what we see is our relative or experimental probability. Those numbers are going to start to become closer and closer to the theoretical probability. So for our first practice problems that we have here, we're going to look at rolling a die, 6-sided die, and we're going to roll it 12 times. For the first problem, we're going to roll it 12 times. And it says that the die lands on the number 3 a total of 4 times out of the 12 times that we roll it. And they ask the question, should you expect that the die is unfair, that there's something wrong going on with the situation? Well, if you're going to roll the die 12 times and the 3 is only 1 out of 6 of those possibilities, the expectation, theoretically that is, the expectation would be that you would have only landed on it 2 times. Right? For every 6 times that you roll the die, you should expect that 3 shows up 1 time. In a perfect system, right? That's the theoretical probability. In a perfect system, that you'd get each number 1 time out of 6 rolls. So if you do 12 rolls, you'd expect it to be 2 times. If you get it 4 times, okay, it happened. It's, we've seen this happen. It's not that weird of a thing. You've played a board game with somebody and you've seen a person roll that same number maybe 4 times in a row, not even just 4 times out of 12, but it might happen, 4 times in a row. So we don't think it's weird. However, according to the law of large numbers, if we were to do the same thing, roll a die, but do it 600 times, not 12, but 600 times, we shouldn't expect the experimental probability to get far from 1 out of 6 chance, which is about 16%. I think it's 16.7%. All right, so it says here that the die lands on the number 3 a total of 293 times. Okay, well, 293 times is basically 300, right? We're trying to give you numbers that aren't like perfectly rounded off, but it basically is 300, right? And 300 out of 600 is half of those times. We shouldn't expect that if we're going to roll the die 600 times, that half of the time it's going to land on a 3. That sounds a little bit suspicious. Okay, so we shouldn't be getting the 3 50% of the times. 50% of the time, we out of 600 rolls, we should have gotten it about 100 times. It doesn't have to be exactly 100, right? But if you get something like 90, maybe even 85, like 85 to 130, we shouldn't think that that's too weird. But once you're getting closer to like 50%, where something should be about 16%, that seems a little bit suspicious. Now, what does that mean for the die to be unfair? That it might be weighted on one side or another. I don't really know on that end of it, but something is off in the situation. All right, so who really cares about the law of large numbers? Well, anybody who has a lot of money riding on chance. That's who. What we're going to do in this activity is look at 2 cases that fit that description, companies, entities that there's a sense of gambling involved in what they're doing and a lot of money is at stake for it. Okay, so what they're going to look at is the law of large numbers, thinking that if they have enough events occurring, that things become favorable to them. The 2 things that we're going to be looking at, or the 2 like companies or entities that we're going to do, are going to be insurance companies, right? Because they're going to, like, you pay for insurance, and if you make a claim, the company's going to have to pay a lot of money out. So they need to make sure that they're selling the policies for the right amount of money that encourages people to buy the policy, but also doesn't make them bankrupt because they got to pay out too much money. And then the other one that we're going to look at is going to be the lottery. Of course, that one's got a lot of money riding on it as well. All right, so what exactly is expected value, and how does it relate to the law of large numbers, and how do these companies actually apply it to make sure that they're going to make profits? Here it says that the expected value is a calculation that considers the value of each option along with the probability of each option occurring. Probably doesn't make a whole lot of sense just when you're reading in the text. So let's take a look at what the formula shows us. And you see this at the end of the next page here. Okay, so expected value, it is a calculation. It's going to be a number that we get back as a response that any of these businesses or so insurance companies or the lottery, what they want to see here. In any process, let's take, even though we're going to talk about the insurance company first, let's talk about the lottery for a moment here. There's these different events that occur. There's a person who has to go and purchase a lottery ticket. Okay, so that's the event. That first event is, which is going to be both of these 2 things here together. That first event is the person who goes out and buys a lottery ticket. There's a cost that goes along with it, like maybe it's a $1 ticket that they have to pay for it, right? There's also a probability of that happening. Now, in this case, and it sounds a little funny at the beginning because we haven't done any examples yet, but the probability that a person buys a ticket is that they've actually handed the money over is 100%. They've actually bought the ticket. So we're not thinking about whether somebody's deciding if they're going to buy it and they already bought it. All right, so there's a probability that when with the person, they bought the ticket, it's worth $1. All right, and then there's these other events that follow after that one, which is going to be like the payout. If you win the jackpot, which might be $1 million, there's a cost to that, but there's also a probability that that's going to even happen, which is going to be very, very small. And then there's going to be even others. So it doesn't just have to be 2 things here. We can have another plus and a couple more parentheses that are going to have like a different payout price, a different prize, and a probability that goes with that one. And then there's going to be another prize and a probability that goes with that one, and so on. And what we do is we multiply all the values. In the case of, well, in all the problems we're going to look at today, they're all dollar values, okay? You're going to multiply that dollar value by the probability that it's going to occur, and then you're going to add them all up together, and you're going to get an overall value, which is called the expected value. All right, coming back to problem number 3, we're going to look at a very simple policy that an insurance company offers. The policy will pay the holder $100,000 in the event that he or she has to lose his job or her job to serious illness. Okay, if a person gets too sick to work, the policy is going to pay them $100,000. Okay, and that's the only thing that this policy actually pays out. So it's a real simple example that we get to look at here. All right, now to purchase that policy, the person has to pay $250. Okay, so there's a sense of gamble like in this whole situation here that, for the person who purchases the policy, $250, it's, if you lose $250 because you never have to make that claim on it, which is, probably better anyway, you don't want to be sick, but $250 isn't a big loss. However, if that person buys that policy for $250 and they make that claim, the insurance company is going to have to pay out $100,000. So you can subtract the numbers and see what the difference would be in that one. So there's a big gamble in the insurance company's business. But here's other information that they know. I don't know if it says where they got the data, but it says previous data shows that the probability a person is going to need to make this claim is going to be 1 out of 500. Okay, 1 out of 500 people are going to make that claim. So now what we want to do is figure out, well, is that a low enough odds that the insurance company should expect, there's your expected value, should expect to make money, or is it not, and they shouldn't actually sell the policies, that stuff. So that's what we're going to start looking at now. All right, the beginning, like this first event to me is always the hardest one to explain until you see the whole thing worked out. There's a person who decides to purchase a policy. That's the first event. A person decides to purchase that policy, and that person is going to pay $250 for that policy. Okay, there has to be a probability that gets assigned to that as well. But the probability of the person purchasing that policy is going to be 100%, because we're looking at this from the perspective that they've already bought it. We're not looking at it as whether or not somebody's trying to decide if they want to buy it. So we're starting investigating this at the moment that the person has paid the $250. So there's a 100% chance that that money is going to exist in this whole situation, and that money is going to go to the insurance company. On the other hand, there's another event that can occur as well, which is the policy holder making the claim that they got sick and they can't work, and they're going to get that money paid out. So the other event is the $100,000 that could get paid out to the person. Okay, now we're going to look at all of this from the perspective of the insurance company. So the insurance company is going to look at the $250 as positive money coming in, but they're going to look at the $100,000 as negative money that's going to be going out. And that's what this part here says. All right, now this is an assured deal, right? The $250 is 100%. They already got the money, $250. The $100,000 going out is going to be 1 out of a 500 chance, which in its decimal form, so just dividing 1 by 500 is a 0.002 value. That's the same thing as 0.2%, by the way. So if you move the decimal over, that gives you less than 1%, but we're going to keep it in decimal form for the sake of calculations. All right, so at the bottom of the page, I already mentioned what the equation looks like. You've got the values of the events and the probabilities that go along with them, and they're going to get multiplied. I don't think I said that earlier, but they're going to get multiplied together. Okay, so in the first event, there's the $250, which is going to get multiplied by 1 or 100%, because it happens. So it is. The second event is the $100,000 getting paid out, so that's going to be treated as a negative number. The probability of that occurring is going to be 0.002. So these numbers are going to get multiplied together. These multiply together to give you 250. These are going to multiply together to give you, I have the work down here to the side, they're going to multiply to give you 200. So if we then complete the equation, which is subtracting the 200 from 250, you're going to get a difference of 50. And we call that the expected value. So even though the policy sells at $250 and the payout can be as great as $100,000, since the probability of that payout is only 0.2%, a small amount, a very small amount, when you multiply these together, we look at the payout as being $200, which leaves the insurance company with $50, the expected value. Okay. But if you're only going to sell one policy, it's still a huge gamble, right? Most likely, because it's 499 out of 500 times that the company's just going to keep the $250 and that's it. But if they got that one person who makes that claim, they're going to end up losing a whole lot of money. Okay, so question C here says, is the insurance company guaranteed to make a profit on a sale of one policy? Absolutely not, right? Most likely, the odds are in their favor that they're going to keep the $250. But if that one person is the one who makes that claim, they're going to lose $99,750. They're going to lose a lot on there. Okay, so what do? They sell lots and lots of policies. Okay, and by lots of policies, we're not talking like 10 policies. We're talking at least 500 to match the theoretical probability that we have. Well, I guess it's technically experimental probability because they got data to use that. They're going to have to sell at least 500 policies to even, somewhat play it safe. But as a company, they're probably going to try and sell like 1 million policies. Hence, the law of large numbers. There's a chance that the first couple people that you sell a policy to are going to make that claim, and it's going to be bad news. But if we sell enough policies, we use the law of large numbers to sell enough policies, then it all starts to go towards the theoretical probability, which would be making on average $50 per policy. All right, there's a couple things here that I want to go over a little bit more. At the very bottom of this, I wrote down that we should imagine selling 500 policies, just to give like sort of thought on it. Now, that doesn't represent like a large number. I'm just saying imagine 500 policies because we had a 1 out of 500 chance that a person is going to make that large claim. So let's just look at what happens with 500 policies being sold. Okay, so the company sells 500 policies and they sell them each for $250. That's going to bring in $125,000. But based on previous data, we expect that one of those 500, and it's an expectation, one of those 500 people is going to make that claim for the $100,000, which means that the company is going to need to pay out $100,000. That'll leave them with $25,000. Okay. Now remember that to get that $25,000, they had to sell 500 policies. So now, if we divide that by 500, we're going to get the $50 that we saw here, and that's telling us now what we expect on average per policy that we sell. So if we do sell a lot of policies, it's going to start to balance off at each of those policies being a profit of $50. All right, one last thing that I wanted to cover before I go on to what would be the next problem. What I put in the box right here is kind of a simplified down version of the equation. All this stuff is there, but just kind of condensed into how you'll actually see it on paper when you're writing it up. Most of our expected value things are going to have positive numbers versus negative values, and it really just depends on the perspective of the problem. So if this is from the perspective of the insurance company, they look at the 250 as a positive. They look at any payouts as negative numbers. So whatever they sell the policy for, it is going to get multiplied by 1, but you don't really need to do that in the math. You can just say, okay, the company's got $250 coming in for the policy, so just write that down, and then it's going to be a takeaway of $100,000 multiplied by the probability that goes along with that one. And if they had other parts to the policy, like maybe a 1 out of 1,000 chance somebody's going to make a certain claim worth a certain amount, you could then have another subtraction and some multiplication going on back here. But just in general, this is what the math might look like if you're not filling in all the blanks, and that's what I wanted to show you there. For question number 4, this is the other big example that we're going to look at. So we did insurance company, and next what we're going to look at is the lottery. One of the big things that the lottery is definitely going to show us is how you can have a lot of different events involved. So for the insurance company, we looked at it where there's only a single type of a claim that was available for the policy. But there's all kinds of different claims that could be like written into certain policies, and they can get much more complex, right? The lottery sort of has, like, if we're talking like, what is this one here? This is your basic Lotto Texas, where you're going to choose 6 numbers out of 54, and depending on how many of the numbers you get a prize. So there's a lot of different payouts that are available. We didn't see that in the insurance one, but it is possible to see problems that involve different types of payouts for the insurance companies. All right, another thing that's a little bit different about this example versus the insurance one, which is really good for us to see, is that this is going to be looked at from the perspective of the person who bought the ticket, not by the company like Texas Lotto. I think that's the name of their company. So in the previous problem, we looked at the purchase of a policy as being a positive number because we're looking at it as the perspective of the insurance company. Here, this is going to be the perspective of the person who's playing the game. So they look at that $1 that they pay for the ticket as being a negative number, but then any payout as being a positive. So flip-flop of it, and it doesn't really make much of a difference in the problems as long as you understand, like, when you're doing the problem, that some things are positive and some are negative, and you just interpret those numbers at the very end. All right, so the first event that occurs for the lottery is buying the ticket. The person who buys the ticket is going to look at that as a negative $1, and there's 100% probability of that happening because they just bought the ticket. So you're in that little weird part there, but just go ahead and think that you start with a negative $1. All right, and then you've got all these cash prizes here that have different probabilities of them actually occurring. All right, so for getting 3 out of 6 numbers, the probability of that actually happening is 1 out of 75. And the prize that the company is going to give out is $3 for that. So we don't have everything written out here, but I want to, I guess, kind of go back and point at the formula. All right, you could look at that as being this part of the formula. The value of that is going to be $3, and the probability is going to be 1 out of 75. So we need to multiply those numbers together. Okay, and that's what this column is going to have. You're multiplying the prize by the probability. All right, now a really easy way to do this, in case you have more probability, in case you have more lottery problems like this, where the probabilities are fractions, when you multiply the 3 times the 1 over 75, you can really just multiply the 3 to the numerator, which means 3 times 1. So you get 3 divided by 75. You can literally just move that number on top of the fraction because they're all going to be 1 out of, or 1 to whatever number. So you can just take the prize amounts and put those in the numerators and then evaluate them. Okay, so that one comes out as 0.04. All right, and then you'll do the same thing for all of these. We got 50 that we can divide by 1,526, which is going to give you 0.03 and some change that I had there. I'll go ahead and just type in all of these here just to make sure I didn't make any mistakes along the way. That looks pretty good. All right, and then when you get to the jackpot, you got 14.75 million. That means you're going to have 14, and then there should be 6 more place values of those. So you got 14, 7, 5, 0, 1, 2, 3. All right, so that would be 14.75 million. We'll divide that by 25827,165, which is going to give you 0.57, so on. There we go. All right, so these are going to be all the expected values. One thing I do want to point out, because I remember this a long time ago when I first did one of these problems, is that you want to understand that these are not probabilities over here. These are values that go along with them. These are the probabilities. So the odds of winning like getting more and more the numbers right, is becoming less, right? You're dividing 1 by that. However, because of the prize amounts that are associated with them, you may see that number appears larger than the other numbers that are here, because this is the payout. This is how we entice people to play the game. We offer them a big prize, and it might not be like as reflective to the probabilities here, but I want to make sure that you understand these numbers are getting larger, even though the odds are getting harder, because the prizes that are corresponding to them are also getting larger, and that's just how all this was decided. But the thing is when they decided what all these prize amounts were going to be, and they're doing all this math just like we're doing it here, they just need to make sure that the expected value comes back in the favor of the lottery. So now we're going to add all these up. That's, it's the same concept to taking that product and adding it to this product and then adding it to the next one and so on, for everything that we have. So you got a -1. So you're already, this is the person who bought the ticket. They're at -1, but then these are all positive numbers because these all represent payouts that would go to them. And in the end, this is what we assign the expected value as a -0.33 or like -33 cents. Okay, now when you play the game, you can't lose 33 cents if you buy one ticket. But the thing is, we're looking at this from the perspective of law of large numbers, with that concept in mind that if people buy lots of tickets, like not even 100 tickets, you can do the math with it, but due to the prize amounts, it's a little bit weird. But you could think that if you bought 100 tickets and you paid, if you paid $100 out to play the game, that in the end, it's going to feel like you lost $33 out of it. Oh, it does talk about buying 100 tickets right here. I was just trying to wing it, and it was right there as the next question. Okay, so you pay out $100, buy the tickets. You're going to get back some money in return, which will be in the form of some of these prize amounts. But in the end, it's going to feel like you came back with $67 from the 100 that you spent. So you actually lose 33. Now you think about all the people that would be in Texas that would be playing the game, hundreds of thousands of people that for every ticket, the lotto company is looking at their expected value of gaining 33 cents for every ticket, or for every 100 tickets gaining $33. So as long as they sell enough tickets, large numbers will take the expected value to that amount or that amount, and that's how the company decides on all their prize amounts. They make sure that in the end, their expected value is positive, where the ticket holders will be negative. All right, for problem number 5, we're going to talk about one more example of expected value, which in this case is going to be referred to as the house edge. We have a picture of a roulette wheel here, and we're going to be asked to calculate the house edge for a $1 bet on red. Okay, so house edge. It's basically the same thing as expected value, with just 2 little differences that I can identify for them. One is the expected value is going to be based off of $1 bet. And the reason I think that they do this is so that no matter what game that we're talking about at the casino, if you bring it down to a scale of a $1 bet, then you can do comparisons of all the different games that are there. So it's sort of like the concept of percentages and get them all on the same scale. Okay, now that really shouldn't affect much, because when you do the calculations, you just pretend that a person makes a $1 bet all the time, and that gives you your house edge, and then you can multiply it by whatever factor you need to figure out the true winnings. But the $1 bet is going to help us get the expected value. The other thing about this one is your first event is not going to be 100%, which is how it shows up in the other 2 examples that we look at, and we'll see that in just a moment. All right, so the roulette wheel has 38 numbers on it. There's going to be 18 black, there's going to be 18 that are red, and then there's going to be 2 of them that are green. Okay, so 18 and 18 is going to add up to 36. And so there's 38 because that's the other 2, which are the greens. The green numbers are going to be used to sort of offset the like 50-50 probability of the red and the black. So if we place a bet on red, the likelihood of winning from that is going to be slightly underneath 50%. All right, so let's do a calculation on that then. What is the house edge on a $1 bet for red? All right, now all this is coming from the perspective of the casino. That means that if it lands on either the green or the black, which is not red, then the casino gets the money, so that's a positive number. But if it lands on red, then we look at that as negative. Okay, so there's a $1 bet that's happening. The casino is going to get that $1 bet if it doesn't land on red. So the probability of not landing on red is going to be 20 out of 38. That's the 18 and the 2 together. Okay, so the probability that the house is going to keep the money is going to be 20 out of 38, and they'll get multiplied. All right, now the person who made the bet, they could get $1, so that's money going away from the casino, so we see it as negative, but they can get $1 if it lands on red, and the probability of landing on red is 18 out of 38. So obviously these are not like the same numbers, so it's not a perfectly fair game, but we all know that when you place the bet, because we know that there's the greens on there. Okay, but if we do the calculations, this one actually turns out to be really easy with the math, because you're just going to multiply 1 by each of these odds. They also both have the same denominator, so real quickly it simplifies to just 20 over 38 minus 18 over 38. Okay, and when you subtract fractions, you can just subtract the numerators if your denominators are the same, which is going to give you 2 out of 38, which evaluates as 0.05. And some change there, but if you're going to turn it into money, we could say that the house can expect to gain 5 cents per dollar that is bet on red. All right, the last thing that we're going to talk about is gambler's fallacy. Simply put, what it is when somebody thinks that they're on a streak, then they feel like it's going to switch sometime soon. For example, I got my coin, right? I think that's what they talk about here. If I got my coin and I flip heads 5 times in a row, heads, 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 heads. That's exactly what it said there. If I flip heads 5 times in a row, in my mind, I think, uh-oh, that's too many times in a row. Next time I flip it, it's going to end up on tails. And then if it lands on heads again, I'm like, uh-oh, now it's really going to land on tails the next time. Okay, but the truth is that every time you flip the coin, there's a 50-50 probability of landing on heads or tails. So it can continue to keep landing on heads. The weird thing is it's how we perceive the whole situation. Okay, so here's 2 situations of flipping the coin 5 times. 5 times heads in a row, and then you have another one that was heads, tails, tails, heads, tails. And in our minds, we recognize that one as being weird or unusual, like, whoa, it landed on heads 5 times in a row. That's crazy, right? Never landed on a tails. And we think of this as like a typical thing that would happen. But the truth is the probability of this one or that one happening is exactly the same. And it's when you pay attention to the fact that this is a very particular sequence. We generally see it like on our own, we look at it and we see it as it's a mix of heads and tails. Well, yeah, normally that's what we feel is going to happen. But this is a very strict sequence that it lands on heads, then it lands on tails twice, it goes back to heads, then it lands on tails the 5th time. That is a unique sequence, a very unique sequence, okay? And if it's a unique sequence, just like landing on heads, then 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 their probabilities are identical to each other. All right, B and C. We flipped it 5 times. I don't know if we're building off of the heads 5 times in a row or not. But when we flip it a 6th time here, what is the probability that it lands on tails? 50%. It doesn't matter that it's the 6th flip. It doesn't matter if it's the 6th flip or if it's the 100th flip after having 99 heads in a row. Every flip is an independent event, and landing on tails is 50%, which means that the probability that the next one's going to land on, I just realized here we got 2 different people that are doing it. Okay. But the answers to the questions, I just realized that I really wasn't paying attention to the original problem. You have two different people that are flipping the coins, and that's how we got our sequences. Okay. Well, the answers to both of these are the same thing anyway. It's going to be 50%. Because every time you flip the coin, it doesn't matter what happened before it. That flip at that moment is its own event.